We have sent spacecraft to every planet in this solar system. Rovers are driving across Mars right now. A probe fell through Saturn's clouds. We photographed Pluto from less than 8,000 miles away, a frozen rock 3.5 billion miles from Earth. We have done all of that. But there is one direction we have barely touched. One region of space that should be the easiest to reach. It's right there, directly overhead. And it turns out to be one of the hardest destinations in the entire solar system. Straight up, out of the flat disk all the planets share. Directly above or below the Sun. The vertical exit from our solar system. It sounds trivial. Just point the rocket upward and go. Physics will not let you. What follows is the full story. You'll understand why escaping vertically is harder than going to Pluto. You'll see what's waiting up there if we ever manage the trip. And you'll see the bizarre maneuver scientists are now considering, where a spacecraft has to first fall toward the Sun before it can ever climb away from it. The prison of orbital velocity. To understand why going straight up is nearly impossible, you have to start with a fact most people never think about. You are moving right now. Not just the Earth turning beneath your feet. The entire planet, you, the ground, the oceans, the atmosphere, is hurtling around the Sun at roughly 30 kilometers per second. That's about 67,000 miles per hour. Every single second, your planet travels 30 kilometers sideways through space. This has been going on for 4.6 billion years. And every rocket we have ever launched from Earth inherits that motion the moment it leaves the ground. When NASA or SpaceX sends a probe into deep space, that probe is not starting from rest. It launches already carrying 30 kilometers per second of sideways velocity, borrowed from the planet it came from. Most of the time, this is a tremendous gift. Want to reach Mars? That sideways speed does most of the work. You just need a few extra kilometers per second nudged in the right direction, and orbital mechanics curves your path to meet the red planet. The same logic gets you to Jupiter, Saturn, even Pluto. The existing motion in the plane of the solar system is your engine. Now ask a different question. What if you don't want to go around? What if you want to go up? That sideways motion you inherited, all 30 kilometers per second of it, now becomes your enemy. To travel perpendicular to the plane, you can't just add velocity upward. You first have to cancel the velocity you already have. Every single kilometer per second of sideways motion has to be eliminated before your spacecraft can even begin to climb. Mission planners measure the energy cost of spaceflight in something called delta V. The total change in velocity a spacecraft has to produce on its own. Getting from Earth orbit to Mars requires roughly 4 kilometers per second of delta V. A mission to Jupiter needs a little more. Going straight up, out of the plane of the planets? Roughly 30 kilometers per second. Almost 10 times what it takes to reach Mars. Let that sink in. Reaching Pluto, a world 3.5 billion miles away, a journey that takes nearly a decade, requires less energy than reaching a point just a few million miles directly above the Sun's North Pole. This is the prison. Earth's orbital velocity hands us free speed in one direction and walls us inside a flat disk. We can hop to other worlds. We can cross billions of miles of empty space. But the moment we try to leave the plane itself, we have to fight the accumulated momentum of the entire solar system's history. It is one of the most counterintuitive facts in all of astrodynamics. And it explains why, after more than 60 years of spaceflight, humans have barely scratched the vertical exit. The mystery at the Sun's poles. Because the vertical escape is so expensive, almost no spacecraft has ever made the attempt. Which means almost everything that happens directly above or below the Sun remains, as of 2026, completely unexplored. Think about what we have managed to photograph. We have detailed maps of Mars, a world tens of millions of miles away. We have high-resolution images of Pluto's surface, taken from less than 8,000 miles. We have seen the rings of Saturn up close, the volcanic eruptions on Jupiter's moon Io, the nitrogen geysers of Triton. We have photographed the nucleus of a comet from inside its own halo. And yet the poles of our own sun, the closest and most important star in the universe, just 93 million miles away, have barely been seen. This is not a trivial gap in our knowledge. The polar regions of the sun are where some of the most powerful and consequential solar activity originates. The fastest solar winds pour outward from structures called polar coronal holes, streams of charged particles racing outward at 700 to 800 kilometers per second. The sun's magnetic field reverses itself every 11 years through processes that begin at the poles. The entire space weather environment of our solar system, the radiation storms that threaten satellites, disrupt power grids, and expose astronauts to danger, is shaped by what happens above and below our star's equator. We have been studying all of this almost entirely from the side. Like trying to understand the full weather of a planet by standing only at its equator and never looking north or south. There have been only 2 missions that ever achieved any real polar view of the sun. The first was Ulysses, launched in 1990 by NASA and the European Space Agency. To escape the plane of the planets, Ulysses couldn't go straight up. Instead, it flew all the way out to Jupiter first, used the gas giant's enormous gravity as a slingshot, and bent its trajectory nearly 80 degrees out of the ecliptic. It then fell back inward toward the sun on a dramatically tilted orbit. The mission succeeded. Ulysses gave us the first direct measurements of the fast solar wind streaming from the polar coronal holes. But it was built with 1980s technology. It had no cameras capable of actually imaging the poles. We learned what conditions existed there, but we never truly saw them. The second mission is ongoing right now. Solar Orbiter, a European Space Agency probe launched in 2020, has been gradually tilting its orbit higher using a series of gravity assists from Venus. In early 2025, it returned the first actual photographs of the sun's south pole ever captured in human history. What those images showed stunned scientists. A chaotic, magnetically tangled region, violent and layered and nothing like the smoother solar surface visible from Earth. Until last year, no human being, no robot, had ever seen what the top of our own sun looks like. Not really. Not from above. The shape of our bubble. There is a second reason the vertical exit matters, and it has nothing to do with the sun itself. We do not know what our own solar system looks like from the outside. Not really. We have never seen it. Surrounding the sun is a vast structure called the heliosphere, an enormous bubble carved into the surrounding interstellar medium by the constant pressure of the solar wind. Everything we know lives inside this bubble. Every planet, every comet, every spacecraft humans have ever launched. Outside its boundary, called the heliopause, lies true interstellar space, a harsh environment thick with cosmic rays and high-energy particles that our bubble quietly shields us from. For decades, astronomers assumed the heliosphere was shaped roughly like a comet. A rounded nose pushing forward in the direction of our movement through the galaxy, with a long trailing tail streaming behind. It was a reasonable assumption. It was the standard model, printed in textbooks, illustrated in diagrams. It was probably wrong. In 2020, a research team led by astrophysicist Merav Ofer at Boston University published a new model built from NASA data, and it suggested something dramatically different. The heliosphere may not have a long tail at all. Instead, it may look something like a deflated croissant, a curved, lobed central structure with 2 short jets curling away from the sides. Compact, asymmetric, nothing like the comet shape taught for generations. The reason we cannot confirm either model is simple. We have never seen our bubble from the outside. The Voyager spacecraft, both of them, crossed the heliopause in the 2010s, becoming the first human-made objects to reach interstellar space. This was an extraordinary achievement. But both Voyagers crossed the boundary almost horizontally, staying close to the plane of the planets. Their measurements are enormously valuable. But they are essentially point samples taken from the edge of one narrow slice of the structure. To actually map the shape of the heliosphere, you would need a probe positioned well outside the ecliptic plane, looking back at the structure from above or below. From that vantage point, you could measure how the boundary curves, where it bulges, whether the tail exists, and how long it truly is. You could answer, for the first time, what shape our home in the galaxy actually takes. There is a NASA mission called IMAP, the Interstellar Mapping and Acceleration Probe, currently designed to refine our understanding of the heliosphere from the inside. But for a true external view, the only answer is the vertical exit. A probe that climbs directly above the plane of the solar system could look back and photograph our heliosphere the same way the Apollo astronauts photographed Earth. Whole, complete, real. We live inside this structure. We depend on it for protection. And as of today, we have no idea what it actually looks like. To climb, you must first fall. So how do you actually solve this problem? You cannot simply build a bigger rocket. The energy required to cancel Earth's orbital velocity is too enormous for any reasonable fuel load. Even the most powerful launch vehicles ever conceived would run dry long before they made meaningful progress out of the plane. There is a solution. It is counterintuitive enough that it sounds like a trick. But the physics is real, and engineers are now taking it seriously. It is called the solar oberth maneuver. The idea works in exactly the opposite direction from what you would expect. Instead of pointing your spacecraft upward and trying to climb, you do the reverse. You aim it toward the sun. You let it fall inward, accelerating under the pull of the sun's gravity, until at its closest approach it is moving at extraordinary speed. Potentially more than 100 kilometers per second. Possibly much faster with the right trajectory. Then, at exactly that moment of peak speed, you fire your engines. Why? Because of a principle first described by the German physicist Hermann Oberth in 1929. A rocket burn is dramatically more efficient when performed at high velocity deep inside a gravitational well. The same amount of fuel that would produce a modest increase in speed in empty space produces a massive increase in total orbital energy when burned at perihelion, the closest point to the sun. The result is a slingshot without the slingshot. You carry the fuel from Earth, fall toward the sun to gain extreme velocity, burn everything at the moment it matters most, and suddenly your spacecraft is moving fast enough to climb straight out of the ecliptic plane and head toward the solar poles, or out of the solar system entirely. The dive becomes the launch pad. Solar sails offer another path, slower but fuel-free. Mission concepts like the proposed Solar Polar Imager and the High-Inclination Solar Mission envision enormous reflective sheets, thousands of square meters of thin metallic film, that use the continuous pressure of sunlight to gradually tilt a spacecraft's orbit. No propellant, just photons pushing steadily for years, spiraling the craft to higher and higher inclinations. The most ambitious architectures combine both. A spacecraft deploys a solar sail to spiral inward toward the sun, gaining both altitude and speed, then performs the Oberth burn at perihelion to redirect its energy vertically. It continues riding the sail outward into the polar regions. This is the kind of mission that astrodynamicists now believe could finally give us the view that has been missing from human knowledge since the beginning of spaceflight. From directly above the sun, the solar system reveals itself as the flat disk it truly is. Planets in their ancient ring, the dust of billions of years hugging the plane, the heliosphere wrapped around all of it in its true shape. No human or machine has ever sent back that photograph. The most obvious direction in the sky is the last frontier we haven't reached. No human or machine has ever sent back that photograph. The most obvious direction in the sky is the last frontier we haven't reached. And if that blew your mind even a little, subscribe. Because we're just getting started.